We get commutativity of addition. Commutativity is the word we use to describe when the order of our addition doesn't matter. If we add B to A or if we add A to B, those quantities are equal to each other. What else? This is an additive identity. So there's an existence of an additive identity. That is some quantity in this Z mod n that we can add to any other element. So A is representing some general element Z mod n. It's a quantity we can add to A, and we get A back identically. So one more time, that's why we say additive identity. 0, that's the thing we call our additive identity, because we can add it to any element and get that element back identically. And that's what we're used to in normal integers. 0 is our 0 element, our additive identity. We have negatives. So when we saw in our tables, we saw negatives of each other. Negatives of each other are just solutions to the equation. So the negative of A is just, what do we add to A to get 0? Same thing in normal integers, and maybe you haven't considered it, like additive inverse of 2 is negative 2. It's the quantity you can add to 2 and get 0. So that's what we're going to think about it in our abstraction. So this is existence of additive inverses. All right. So the thing we add to A and get our additive identity. Closure under multiplication. Same thing. We multiply two elements in the set, we still stay in the set. We have associativity of multiplication. This is our distributive property, how addition and multiplication, or distributivity, maybe I should say, how multiplication and addition play together, interact together. Notice one important thing. We haven't even broached these yet. We haven't talked about those yet. The order in which I'm multiplying this C, it stays consistent when I distribute. I'm multiplying C on the right. A plus B times C is A times C. So I'm multiplying C on the right. A times C, C is multiplied on the right. C times B. Linear algebra, matrix multiplication, order mattered. We're going to take examples from linear algebra, and we're not always going to get this next property that we have commutativity of multiplication. It's nice for integers. It's nice for integers mod n, and we do in fact get it. But you can keep in the back of your mind commutativity of multiplication. And what I'll just say is we're going to see in part 2 of this story the complete generality of what a structure that satisfies these first properties is that we could also distribute, actually no, I had both of them. All right, yeah, I was focusing on when we were multiplying C on the right. When we distribute, and we're distributing left multiplication over some sum, notice A times B on the left, A times C, we're multiplying on the left. So notice distributivity, 1 on our left side, 1 on our right side. Order matters. We're going to internalize that. So far, we haven't seen too many. You can just take a preview and store it maybe in the back of your brain. Order of multiplication is going to matter, just like multiplication of matrices. And lastly, we have a 1 element, something that we can multiply by A and get A back identically. Maybe I was missing that kind of A like I had. And we refer to those things as the thing we can multiply by and get A back identically. Call this 1 is a multiplicative identity. Awesome. So the additive identity, it's the thing you add, it's the quantity you add to an element to get that element back identically. Multiplicative identity, the quantity you multiply by to get that quantity back identically. All right. So these properties also satisfied by the integers. We didn't get too far from it. We definitely defined a new structure, new algebraic structure, where you have addition and multiplication, but we didn't get too far from it. All right, so to help us kind of compare and contrast with our normal integers, let's define the following quantities, or following notions. An element, we're working in Z mod n, so an element in Z mod n is called a unit if the equation ax equals 1 has a solution. In other words, that means there's some other element that we can multiply by and get 1. Just like we thought about, so let's I think I mentioned, we talked about additive inverses. That's the thing we can add and get our additive identity. Just the thing we can multiply a by and get our multiplicative identity. That might be another way to translate this. And it's our inverse. We actually now are getting some properties that we didn't see for normal integers. For normal integers, let's just think about for a second, what's the question? The question is, what are our units for normal integers? 1 and -1 are the only units in Z. Those are the only things that there's a quantity we can multiply by 1 or -1 and get 1 back. The inverse of 1 is 1. Inverse of -1 is 1. Or is -1. -1 times -1 is 1. And so this is a notion you've probably seen maybe more in the real numbers or rational numbers. If we had 2, we might think about its multiplicative inverse as 1/2. It's the thing we can multiply 2 by and get 1. And we're going to see more of these pop up in Z mod n. So we had our nice table. And maybe I'll give an example. How about, we haven't worked with Z mod 7 yet. 3 times 5 is equal to 15. 15 mod 7 is 1. And so we can think about what we're saying here in terms of our definition is 3x equals to 1 has a solution in Z mod 7. So we call 3 a unit. For that reason, 3 is a unit. It's got some quantity we can multiply by and get 1. And we denote, so this is 3 is a unit. And we denote its multiplicative inverse just as we're used to for rational numbers or real numbers. 3 to the -1 is equal to 5. Remember, we're working in Z mod 7. All right. We already have an example listed for us. So let's just, we'll come right back to this and we'll work on zero divisors. Let's just go back into Z mod 6. Z mod 6, again, same definition of units. They are the numbers where we can multiply by something and get 1. What are our units going to be in Z mod 6? Anyone want to think something's a unit? What was the question? Yeah. What numbers are units? And so I'll help recall the definition again. Yeah, thanks for that clarification. What are the units here? A unit is a quantity. It's an element we can multiply something else by it and get 1 back. I think I heard 5. 5 is a unit. 5 times 5 gives us 1. So it's a thing that has a multiplicative inverse. In fact, 5 is its own inverse. 5 times 5 is equal to 1. It's the thing we multiply by to get 1. Let's contrast that a little bit because it's a little funkier, but maybe you've worked with rational numbers. Let's And those might be more familiar to you. The thing we get 1, it's like undoing, it's the inverse of multiplying by 5, we multiply by 1/5. So if we wanted to now work in Z6 and do the inverse of multiplying by 5, we just multiply by 5. It's the thing that we multiply by to get 1. So 5's a unit for sure. Any other numbers that are units? 1. And 1, just like we're used to for regular numbers, is its own inverse. Multiplying by 1, what's like the inverse of that? Multiply by 1. You might notice we said -1 is 5. Makes sense. Okay, -1 should probably be a unit as well. Awesome. Those are our only units. You can see in the rest of these rows, we don't see any 1s appearing. There's not something we can multiply by and get a 1. Kind of seems like these two things are mutually exclusive, maybe we can think about. Either we're going to see some zeros popping up, or we're going to have to see all of our numbers appear once and it be a unit. Okay, so that's what a unit means. Zero divisor, that is something that has a solution, or something that gives a solution when we take the equation ax equals 0. So something, it's an element in Z mod n, where we can multiply something by it and get a 0. In that Z mod 6 example, we'll go back to that multiplication table in just a second. We can think about asking which quantities, which elements in there were things we can multiply by something else and get a 0. So in Z mod 6, I'll give an example of a 0 divisor. 2 times 3 is equal to 0 in Z mod 6. So that implies that 2 is a 0 divisor. Awesome. 2 is a 0 divisor. And so we go back up. Yeah. 2 is a 0 divisor, we see some zeros. 3 is a 0 divisor. 4 is a 0 divisor. And what we see, maybe one property of 0 divisors that I want to now clarify is, why are these 0 divisors? They're sharing some factors with our n. Sharing some factors with our n. So that means we can take some multiple of them between 0 and 5, multiply them by some number between 0 and 5 less than 6, and get some multiple of 6. And so that's what's going on. We'll prove our theorem next, but sometimes it's nice to see a concrete example. So I'll say one more time, 2 features to notice that we're going to finish off today with. Units, that means we can find some multiplicative inverse or something we can multiply by and get 1. And 0 divisors. And those are things we'll show that are going to share some factors with our n that we're modding out by. All right. So before we even, if we're going to be thinking about common divisors with our n that we're modding out by, we might as well take our most straightforward example when we're never going to be able to share common divisors with the n we're modding out by. So let's think about Z mod p when p is a prime. All right. So what is this saying? It's saying what types of elements do we get in Z mod p when p is a prime? When p is a prime, it's saying the equation ax equals 1 always has a solution. Or every element is a unit. Every, and really want to emphasize this, so I'll put it in red. Every, there you go, every non-zero. Every non-zero element is a unit. 0, you multiply anything by 0, you get 0. everything else, you're going to see that row in its multiplication table is going to have a 1 in there. There's going to be some multiplicative inverse. There's going to be some solution to ax equals 1. So you can start writing down some. Take z mod 3. What table do you get? The multiplication table. You might notice all of those rows are always going to have all your values, including a 1. Z mod 4. No, that's not going to be the case. It's not prime. Z mod 5. Yeah, that'll be the case again. So that's what number 2 is saying. Every non-zero element is a unit. Okay, and now this is just an analog of what we said, a prime divides a product. So what does it mean for a product to be equal to 0 in z mod p? This is saying that b times c is congruent to 0, or b times c is divisible by p. And we're just saying b times c divisible by p means that b is divisible by p or c is divisible by p. In our new language for modular arithmetic, whenever we have a product equal to 0 and we're working modulo a prime, one of those factors has to be a 0. Or there are no 0 divisors there. So when z mod p is a prime, you only get units except for 0. 0 is like our 0 element, but everything is a unit. And that's just the same thing as saying there's no 0 divisor. The rest of those rows, the only time you see a 0 appearing in it is when you multiply by 0. All right. Let's prove this. These are all equivalent. So I'll prove 1 implies 2, 2 implies 3, 3 implies 1. So you can see they're all equivalent. This is kind of a nice culmination of all the techniques we've been building up so far. Since p is prime, let's consider the greatest common divisor of a and p. So we want to talk about solutions to this equation, so we're going to be involving some a. Let's think about greatest common divisors. And greatest common divisors always divide both the numbers. It's a common divisor, so the common divisor, it certainly divides p. What did we say about divisors of a prime? What are the possible divisors of a prime? 1 in itself. Okay, whoops, or itself. Okay, we also know greatest common divisors. Divisors have to be less than whatever quantity we're considering. A is an element of z mod p. Elements of z mod p are numbers 0, 1, 2, all the way up to p minus 1. So in particular, a is certainly less than p. And, right? This is an element in z mod p, so we can reduce it and write it as 0, 1, 2, all the way up to p minus 1. And we know that this quantity divides a as well. It divides a, it's got to be less than a. There's no chance our greatest common divisor could be p. Right? I'll put into words what I was just saying. Right? Elements in z mod p, they're the possible remainders we can get, so they're between z and p. Does not include p. And so that implies that this has to be equal to 1. No way it could be. All right. What was our big theorem that we continue to we keep seeming to use about common divisors? How can we write a common divisor in terms of the two quantities we're taking that greatest common divisor of? There's like a 3-word name I gave it. Integral linear combination. Greatest common divisor of a and b can be written as an integral linear combination of a and b. And it implies there exists some integers such that ax plus py equals 1. We're going to keep using this. If you haven't seen it yet, or you're not quite comfortable, I'm going to keep using it, keep using it, keep using it. So might be good to review that too. Okay. And lastly, we want to show that ax equals 1. That's just saying that a times x is congruent to 1 mod p. So we might want to solve for, if we're trying to show a congruence, right? This is telling us a congruence in z mod p. So we want to solve for ax minus 1. I'm going to write it as this way. Negative py I can just express as p times negative y. I just wrote ax minus 1 as an integer multiple of p. That means these two things are congruent modulo p. So in z mod p, those are equal to each other. All right, there's our proof. Kind of a culmination of everything we've used, right? Greatest common divisors, and people call it sometimes like Bézou's lemma, or writing greatest common divisor of a and b as a integral linear combination of a and b. And the rest of the proof follows similarly. So let's wrap that up. So 2 implies 3. This is saying that every element is a unit, means that there are no zero divisors, there are no non-zero zero divisors. All right, so suppose b equals c. If b equals 0, we're all done. Awesome. So let's focus on b non-zero. So if we take some non-zero b, part 2, I was trying to keep it all in. Right, and so we're thinking about b non-zero. We've got some equation. If we wanted to solve for c, you can think about just same intuition you might have with normal real numbers. So we can see what 2 and 3 are. Let's zoom in on the problem at hand. We're trying to show that if bc equals 0, either b equals 0 or c equals 0. If b equals 0, we're done. If b is not 0, we probably want to solve this equation for c. 2 tells us that every non-zero element is a unit. So we just said b is non-zero, so it's a unit. That means it has some multiplicative inverse. We can kind of, I'm going to rephrase this. You might say divide by 0 if you're working with real numbers. Let's translate that into our new language. We can multiply by the multiplicative inverse of b. Let's multiply b by the thing that gives us 1. We have the assumption, too, that everything is a unit, and we can, in fact, do that. Since b is a unit, by 2, b is a unit, or bx equals 1, I believe, precisely is what it says, has a solution. Let's call it b inverse, right? That's how we write our multiplicative inverse. Then multiplying both sides of the equation above. On one hand, b inverse times b is just 1. 1 times c is c. And if we multiply any element times 0, we just get 0. All right, so either b is 0, we're done. If b is non-zero, we use that it's a unit to conclude that c is 0. All right, last one. Got always like limited space on here, but let's use it. I'll remind you, this is saying that every non-zero, there's no non-zero zero divisor, and we want to conclude that we're working in z mod p, and for some prime p. So the thing we know how to work with is we know when we have products equal to 0, at least one of the elements is equal to 0. Sorry. That was our last step. Okay. So one more time, you can kind of think about. We know if we have products equal to 0, at least one of the elements is 0. We want to conclude that's just the equivalent definition of primeness. So we're just going to translate that into primeness. A number is prime if when it divides a product, it divides at least one of the factors. We're just doing that translation we've been doing all along between congruence and divisibility, right? Two numbers are congruent modulo n if their difference is divisible by n. So that's all we're going to do. So suppose we've got some prime dividing a product. We're going to show that that prime divides at least one of the factors. All right. If a prime divides a product, then that is telling us that BC is congruent to 0 modulo P. What does that mean? We just have BC is equal to 0 in Z mod P. So if we treat B and C as elements in Z mod P, their product is equal to 0. All right. 3 tells us that B equals 0 or C equals 0. And so we can think about if B equals 0, this implies that, so as I said, I'll try and make sure I specify to be really clear. If this right here, this expression, we're saying this is an expression ZP. We're treating this as a congruence class. This is a congruence class. If those are the same congruence class, then that means B is congruent to 0 mod P, or P divides B. Awesome. Completely identical thing for C being 0. So what did we start with? We started with P dividing a product and showed that had to imply P divides B or P divides C. And that was our exact condition for primeness. Therefore, P is prime. All right. So I'll leave you with next time, and I'll lay out all of the details in our practice problems. We are a